This is a picture of Bryce Canyon National Park in Utah. I took this picture one April over spring break, and it's at about somewhere between 6 and 8,000 feet above sea level. And so you can see that even in April, there was still plenty of snow at this part of Utah. This is the bedrock or the foundation of some of the areas of Utah. And I wanted to show you this because even though this rock is 60 million years old, it's actually geologically very young, just like geology itself is actually a pretty young science. So what I want to talk about in this segment is really some of the foundations of geology as a science. Geology became a science around the mid-1800s. There were a couple competing ideas, and the one that came out victorious is the reason that geology is a science today. So at the time, there was a very popular concept called catastrophism. It was popularized, and the word probably makes you think very much of this picture, a catastrophe, and it's supposed to. Catastrophism is an idea that was popularized in the 1850s by Bishop James Ussher, who is an Anglican British bishop, and he did something really interesting. He actually used the genealogy of Jesus in the very beginning of the New Testament of the Bible, and he assumed an average age for people that living at that time, and he backtracked and calculated what he thought would be the age of the earth. And he came out with something very precise, something like October 23rd, 4004 BC at 9 a.m., which is monstrously specific. He thought that some of the landscapes, some of the big landscapes that we see on Earth today, like Bryce Canyon or the Grand Canyon, for example, were landscapes that were created in these catastrophes, these biblical scale catastrophes, like Noah's flood, for example. And he also believed that these catastrophes no longer occurred because he never lived through something so large that he could imagine that the Grand Canyon or Bryce Canyon could form as a result of any of those experiences. So the problem with this, and there are catastrophes we know that happen on Earth that greatly change the Earth. However, if they no longer occur, then geology isn't a science. We can't understand the processes and then use them to make predictions like we can all other branches of science. So catastrophes do occur, but they're not always very common. And that is something that's captured in an idea called Uniformitarianism, which is really an important concept in geology. Uniformitarianism was created by a man who's actually seen by many to be the father of modern geology, James Hutton, who actually lived around the same time as James Ussher. So this is not a picture of James Hutton. This is actually a picture of what's called Hutton's Unconformity. We'll learn more about unconformities over the semester. But what you see here is a geologist, and this is an important spot for geologists to visit. I've never been there, but hopefully someday. This is on the coast of Scotland, and what you probably notice here is that the rock layers on the top where this man is standing are tilted at a very different angle than the rocks below. And these are all sandstones for the most part. Hutton lived in Scotland, and he used to walk along these sandstone cliffs right near the ocean, and he found himself one day thinking about how in his life he had noticed some changes at the beach in the sand where he lived. And then he looked at these cliffs of sandstone and said, wow, the earth must be really old, because if I have observed this much in my life and then I see these hundreds of feet of sandstone, well, the earth must be much older than 4004 BC. And he didn't know how old, and he didn't take a guess, but he was right when he said it was old. James Hutton came up with the idea that it had to be old because the only way we could understand the past was actually by understanding the present. So uniformitarianism is the idea that the present is the key to the past, that the processes that we observe today, the processes that we can measure today, are actually things that have occurred in the past. So if we understand what's happening today, then we can interpret by looking at the rock record what happened in the past. This is actually why we take physical geology as geology students first, and then historical geology, so we can study what's happening today and then use that to interpret the past. A more modern example of geology is illustrated here on this very simplistic diagram. So Probably some of you have seen a diagram similar to this before. These are the layers of the Earth. And I didn't put a lot of words on these slides. Hopefully that you'll be able to kind of take notes and keep up with my explanation, and it'll make some sense. So first, let's name the layers of the Earth. And again, this is a really simplistic diagram illustrating the core in the center of the Earth, the Earth's mantle, and then the crust. So we're going to talk about each of these layers in some detail. The core of the Earth is really fascinating. And if you think it's hot, you're right. It is incredibly hot for a few reasons. So part of the reason that the Earth's core is hot is simply because there's so much pressure that's exerted, gravitational pressure that's exerted down toward the core. And so that overlying pressure results in an increased temperature. It's also hot in part because there's a lot of uranium in the core of the Earth, and over time it slowly releases lots of heat. And so that's the second reason that it's hot. The third reason that it's hot is that even though the Earth is 4.5 billion years old, there's still a tiny bit of residual heat from when the Earth first formed and it was being smashed by small planets and asteroids, and that heat is a small part of the core's heat as well. So the core is about 12,000 degrees Fahrenheit hot, which is kind of hard to imagine. We know that the Earth's core is actually subdivided into a solid inner core, which is predominantly made of iron and nickel, and a liquid outer core. So there's lots of different ways that we can infer how the core is sort of composed. We've never been there. We've never even been quite to the base of the crust, but we can use earthquake waves to figure out what's going on inside the Earth. So the liquid outer core is something that is very interesting. Because, again, the core is mostly iron and nickel, the liquid outer core, because it's so hot, flows. And so very much like the boiling in a hot pot on a stove, the iron and nickel in the core, in the liquid outer core, will flow. And that flowing iron and nickel will actually generate the Earth's magnetic field, which is incredibly important. It's important for organisms that migrate. They use the magnetic field. It's important for humans. We use the magnetic field when we are using satellites and GPS. All rely on the magnetic field. And so we have fewer solar winds hit the Earth because the magnetic field actually will deflect them back into outer space. We have the aurora on the Earth in the north and south poles, the aurora borealis, because of interactions between those solar winds and the magnetic field. So very cool, very important, very heavy, dense minerals in the core. Again, iron and nickel, really heavy material. So the mantle here is actually an incredibly important layer of the Earth as well. Over 80% of the volume of the Earth is the mantle. And even though every animation, or most animations you will see of the mantle, illustrate it as a fluid, it is actually a solid rock. It is a solid rock that is very warm though, and it'll actually flow over time in almost a plastic manner. And so, as you might imagine, the material near the lower mantle, near the core boundary, that's the hottest portion. And so what will happen is that just like in your house in the summer, where the hot air rises and cool air sinks, the hot rock in the lower mantle will rise up through the crust, or rise up through the mantle. And when it gets close to the crust, it'll cool off and start to sink back down toward the core. So you're going to watch a little video about that, but that is a heat distribution mechanism. It's called convection. Convection predominantly occurs in the mantle. So I want you to click on these two links, and if you click on the word convection here, that will open one link that will just tell you a little bit more about convection, where hot materials rise and cold materials sink, and there's a video there that uses garbanzo beans to illustrate it. Then if you click on this second video here, what you'll see is something a little bit different. It will show you how convection in Earth's mantle actually ends up driving the movement that we see on the crust of the Earth. And the mantle convection actually ends up causing earthquakes and volcanoes to form on the crust of the Earth. So make sure you watch both of those videos. We're going to do a little activity about convection next, but it's incredibly important. It really does control, to a large extent, what the surface of our Earth looks like. Okay. So again, convection in the mantle results in earthquakes and volcanoes on the crust. The crust of the Earth is divided into two different types of plates. So there are continental plates on the crust of the Earth. Continental plates are generally low density. They are generally pretty thick. They're between 20 to 40 kilometers thick, and they are generally pretty old. So the oldest crust on Earth is a little over 4 billion years old, and that is in northern Canada. There's also some really old chunks in parts of Siberia and in Australia. So it's old, and it is thick and buoyant because it's created mostly with lighter metals, so it tends to float, kind of like an ice cube in a cup. So the other type of crust on Earth is called oceanic crust, and oceanic crust is pretty much the opposite. So where continental crust is low density, oceanic crust is high density. That's because it's mostly made of heavier metals, lots of iron and magnesium, which are heavier metals that make the ocean crust a little bit denser. Where continental crust is thick, oceanic crust is thin. So if continental crust is 20 to 40 kilometers thick, oceanic crust is 2 to 4 on average. And where continental crust is usually pretty old, like millions or billions of years old, the oldest ocean crust we have is about 165-ish million years old. So think about that, 165 million years for oceanic crust, 4 billion years for continental crust. And in general, there are two rocks that I want you to think of when you think of each of these types of crust. So for continental crust, the rock that you want to think of the most is called granite. And granite I will show you a little bit more of in the future. And the rock that you want to think of for oceanic crust is actually called basalt. It's spelled Basalt. And we'll talk a lot about these two types of rocks. Granite is generally light in color because it's made of light metals. And basalt is generally dark in color because it's made of heavier metals. So we're going to explore a little bit more about convection next, and then we'll finally get to talk about rocks. Thanks.